I work at Safran Aircraft Engines. My job is consists on the determination of crack methodologies for engineers. And I would like to present you a simple way to determine the crack propagation life of three-dimensional cracks. One way to compute life in crack propagation is to use wave functions. It is very simple to use to compute stress intensity factor. You only need the stress field of an uncracked structure. So if you have crack propagation law and failure criteria, it is very simple to calculate life, and the time cost is very negligible. The life corresponds to the number of updates in the algorithm of the crack geometry. The problem with that this kind of approach is that if we impose on the structure displacements, the superposition principle doesn't work. The stress intensity factor obtained by this way is much higher than in reality because of the decrease of the stiffness of the structure induced by the crack propagation, and this leads to an decrease of the stresses on the boundary. There is another another problem with this kind of approach. It is the simplifications made on the plane. Here we have a disk. The crack initiates at this point. Here we have a section of the disk. This section is orthogonal to the max principal stress, and we can see that if we want to use weight functions, we have to approximate this geometry by a rectangular plate, and this leads to a stress intensity factor higher than in reality, and so the life could be less than reality. We can use more sophisticated methodologies like a finite element method, boundary element method, or extended finite element method in order to simulate the crack propagation. And for each crack step of the propagation, we need to make a complicated computation. This is accurate in terms of the evolution of the stress intensity factor along the crack front, but the time costs are not negligible, and in fact, the number of crack steps are imposed because if we compute each crack propagation for each loading steps, the time of the cost will be very prohibitive. And to do that, one way is to modify the Paris law by introducing a coefficient alpha in order to obtain crack higher crack extensions. With this kind of method, the crack path can be converged, but the life is often overestimated by this way because we consider that the stress intensity factor is constant between each crack propagation step. In reality, between each propagation steps computed by the finite element method, there is a lot of cycles which can occur. And for each cycle, the stress intensity factor in reality increases like the red curve. And so the true life is less than the life estimated by this kind of method. One way to compute the life accurately is to make a conversion of the three-dimensional information from the 3D crack simulation into a thermodynamically 1D equivalent formulation. The methodology consists on inputting 4 constraints. The first one is an equality of the crack front length for all propagation steps between the 3D formulation and the 1D equivalent formulation. The second constraint is the equality of the energy release rate for each loading cycles and for each crack propagation step obtained by the 3D simulation. The third one consists of equating the crack surface increments between the two formulations, and we want to calculate the life by the same crack propagation law. The reduction of the dimensionality of the problem avoid us to consider the 4 constraints at the same time. So we defined 2 approaches, one energetical and second one geometrical. The first one consists on combining these 2 constraints and this one, and this approach consists on accounting for these 2 and this one. If we take a look on the energy approach, we know the stress intensity factor along each front, so we can compute the energy release rate for each node. And for each cycle, the crack will propagate, and so we can compute a dissipated energy with this formula. Now, here we have the crack propagation law. And by using the 3D, 1D equivalence, it is possible to equalize these 2 energies and to formulate the problem more simply, and finally to obtain an equivalent energy release rate. And so we can obtain an equivalent stress intensity factor. By equating the dissipated energy between each front and between these 2 formulations, it is possible by considering a linear interpolation of the crack front length with 1D equivalent crack length. It is possible to calculate an equivalent crack length increment between 2 fronts. It is possible to do the same thing for the geometrical approach. For each front, we can compute an average crack growth by equating the formulation with the 1D problem. It is possible to obtain also an equivalent stress intensity factor. And by equating the crack surfaces between the 2 formulations, we can compute also an equivalent crack length increment between two consecutive crack steps. At the end of the process, we obtain an evolution of the equivalent stress intensity factor with respect to an equivalent crack length. For example, we have the stress intensity formulation for the two methods presented above for this problem. And as we can see, for this problem, the two formulations give us similar results. And this proves that the problem is converged in crack propagation. And by integrating the crack propagation law by using this formulation, it is possible to obtain at the end the life. It is very simple to use. At the moment, I have to validate this method experimentally. It is not possible for the moment, but I try to validate this method numerically for the moment. For this test, I consider a through crack, and the stress intensity factor for these cracks are obtained with this formula. We consider different crack lengths, and we consider also a problem with a stress intensity factor which depends randomly on the crack length. We suppose that these results were obtained on a 3D formulation.
1 minute.
Thank you. And we test now our methodology, and we find at the end that for this test, we found that the equivalent stress intensity factor obtained by the two approaches give the same results than this formulation. And also, the equivalent crack length corresponds also with this definition of the crack length. So it shows that this method is consistent. And for elliptical cracks, we use a formulation in the literature which gives us the evolution of the stress intensity factor along the crack front for a tension load for a crack in an infinite media. And we find that the equivalent crack length corresponds, in this case, corresponds to the square root of the surface crack divided by P. I think it's not a natural result, but this result is compatible with what was observed by Murakami experimentally, and it is compatible with what Louis obtained with the perturbative method also. So a simple engineering method to obtain a 1D equivalent stress intensity factor solution for complex geometries and loading was presented. It is very simple to use. The integration of the Paris law with this solution allows to obtain robust life estimation, and it is possible to verify very quickly the convergence in crack propagation. But some validations need to be done. Some experimental validations need to be done. Thank you for your attention.